Hey guys, welcome back to AlgoYogi. We are doing graph series, and next problem in the list is a minimum fuel cost to report to the capital. So let's go to LeetCode and read the description. So there is a tree. Also, they have given the definition of the tree, a connected undirected graph with no cycles. So that's basically, this is what distincts a graph from the tree. Well, this structure represents a country network consisting of n cities numbered from 0 to n-1, and there are exactly n-1 roads. Now the capital, by the way, if you notice this detail, that tells you there are no cycle, because if there are n number of nodes and there are n-1 roads, that's the number of roads it needs to connect all the cities together without introducing a cycle. If you add one more edge into it, then you kind of introduce a cycle into it. So the capital city is city 0. You are given a 2D integer array called roads, where this is just like edges, like the other problems, where this at the ith position there is a pair A and B that denotes an incoming, outgoing. This is bidirectional because it's undirected graph, so there is basically outgoing, incoming edge from A to B, B to A. This makes, this goes both ways. Now let me put my phone on silent. All right, so there is a meeting for the representatives of each city. The meeting is in capital city. There is a car in each city. You are given an integer called seats that indicates the number of seats in this car. Well, there is one car in each city, and there are basically one representative in each city. Now a representative can use the car in their own city to travel to the the capital, or they can change the car and ride with another representative, so that the cost of traveling between two cities is minimized. Or they have also given like it's 1 liter of fuel, so we need to basically return the minimum number of liter of fuel to reach the capital city. So I have taken this example right here to understand the problem. Basically we are given n cities, n is 6 cities right here. So 0 to basically 5, these are the cities. And remember, I have drawn it like a tree, although it's just, remember, these are bidirectional roads. So basically there is incoming and outgoing. So 1 and 0, they are connecting both ways. So you can come to 1 from 0, you can also go to 0 from 1. The reason I have drawn it like this is it makes our problem to comprehend really easy for us. Okay, so what are we trying to do? We are trying to basically calculate the minimum number of fuel it will take us to get all our representatives to the city 0, because that is the capital city. Now, what is the problem in running the DFS and getting all of them basically to this 0, which is the capital city? Well, we could run DFS on 0 and basically calculate this number of edges, and then we can just say, okay, you know what, each city has a car, and that car can take the representative. So basically this will take 1 to get to the city. Let's say this will take 1 to get to city, this will take 1 and 2, so this will take 2 liter of fuel, this will take 2 liter of fuel as well, and this will also take 1 liter of fuel. So in total it's taking basically, so 2 to 4, 5, 6 liter of fuel, right? That is the basically if we don't do any carpooling. But what if we could do carpooling? And that's what we have been asked to basically do. We do not want these representatives to basically travel in their own car, because there are cars passing from this city through city 2. So if the representative from 4 is going through 2 to 0 to the capital city, and this car has basically, let's say, seat equals to 2, and it's going through right here, then it can pick up this guy. So it can ask this guy to basically sit in his car and then, or her car, and then they can both drive. So that this guy the node 2 doesn't have to basically waste 1 liter of fuel, right? And this will require, both these nodes will require 2 liter of fuel to get to the city. And this one will still require 2 liter of fuel, but you have saved 1 liter of fuel. Basically, in this case, 2 and 1, and this 1 and 1. So max fuel they need is like now it's 5 rather than 6. So that's what we need to do. So what we are going to do right now is we're gonna run DFS. We're gonna run a DFS from 0 to all its children, and basically ask its children to calculate the fuel, total fuel that they need basically to get to 0. So it's going to ask 1, like running the DFS, then how many passengers are basically traveling with you, and those total number of passengers we will basically divide with the number of seats, because the number of seat can decide that how much fuel you actually need, right? Because let's say it had two more children, let's say right here, and they both will be basically coming here to city 1. So that means they both can travel in their car to here, and they're gonna basically these two representatives right here, although they will waste basically 1 liter of fuel right here, 1 liter of fuel right here, but like once they are here, and now let's say the seat given to us is basically, this max capacity given to us is 3. Now this guy 1, what this guy can do is basically they all can get into one car. So this guy from here, so there are 3 people, so 3 representative divided by 3, and also we can, in math we will basically do ceiling of 3 by 3, so that we get 1. That is the number of car that can travel up, which is like going here, that will take 1 liter of fuel. So traveling one road between 2 cities is like 1 liter of fuel. So now from here they can only use one car to get here, so that will be 1. So 1 plus 1 plus 1, so that will be 3 liter of fuel. But if they were all traveling by themselves, then they will waste like 1, 2, and this one 3, 4, 5. So 5 liter of fuel, but this time it's like 1 plus 1 plus 1. Now that's what we will be doing with all the other cities. We will be basically calling, the 0 will be calling DFS. By the way, we will have to keep track of the parent node that is calling the DFS, so that we are not calling back the DFS on the parent. So we will basically, to DFS we will pass the node that will be calling the DFS on its children, and also the parent that has just called, so that we are not getting in the cycle. So this one we will be calling DFS on 2, then 2 will be calling DFS on 4. This one will be basically asking its child. It doesn't have any children, so it will basically say I have one passenger. So this one passenger divided by the number of seats. So let's say this seat is right now 3, this 3. So that will be basically ceiling will give me 1. So that means I just need one car. So one car will go here, so 1 liter of fuel. We will maintain a result variable that will just keep adding. It's like a global result that will keep accumulating all the number of fuel that we are taking. So this will take 1, it will reach here. Now this one also will do the same process. It will reach here. Now it will have its own one representative, which is 1. So these 3 from here can all of them pool into one car, because the seat capacity is 3. So 3 divided by 3 again right here, then they can go to the capital city, and we will only need 1 liter of fuel. And then here also it will require 1, and remember from here we required 1, 1 and then 1, so 3. So our total cost in getting all these guys to basically capital city would be 3, 4, 5, 6, 7. Remember, in this case I have considered these two as well, right? Don't forget, like I have also I made some node right here added just to understand our problem better. So I think that would be it. It's all about calling the BFS and then taking the seat capacity in consideration that was given to us, right? I'm gonna basically switch now here. So you remember this seat capacity? Yes, that's what I was talking about. Now let's write down the code. It's going to be pretty easy. I think this problem comes off like really hard in the beginning, but like once you draw this graph or tree like as a tree itself, with the outgoing edges, and then you are calling DFS on the child node are collecting the representative from its neighboring node or child node, and then collecting them together, calculating the ceiling passenger. It's the fuel actually. You're calculating the total number of passengers collected at one node divided by the key seats capacity, and then taking the ceiling. That's what will give you the number of cars, and number of cars to get to the parent node will give you the number of fuel. I hope that's just understandable. So let's first of all, basic step is just creating the graph. So default dict of list, calling this graph, and let's fill it up. So for A and B, I would say, and B in roads, this is like edges for us. We have worked with edges all the time creating the graph. Basically it's bi-directional, so we will be adding it to A to B, B to A's parent, well, A is neighbor, so A's neighbor, and then we will doing the vice versa. Awesome. Okay, so now our graph is ready. This adjacency list is ready. All right, so what do we want to do? Let's have like a global variable. I'm gonna just call it a result variable or total fuel, and I'm gonna have it like as an array. So initially assigning so that it's accessible inside my DFS function that I will be writing here. So this DFS will be taking the node, and then it will also take basically parent node. Just remember, we are taking it just to avoid the cycle. So here what I'll be doing is I will be actually return total fuel, and basically this element. But before that, let's collect all the fuel, right? How do you collect all the fuel? Well, you just run the DFS on what? 0. That's my source node. That will be basically collecting all going DFS until all the leaf nodes, collecting all the passengers, coming back, and you don't have to do it. We will do everything within DFS. That is basically updating it with the total number of fuel. And let's see how we're doing. So this is the parent node I'm passing. So 0 doesn't have any parent, so that's why like this will never be a problem for us. Right, so here we just need to basically collect all the passengers or representatives. So I'm just gonna call it representatives. Initially it's gonna be 0. Then we are going to basically go to all the neighbors of, or I'm gonna call it child. So child of, because it's a tree and child seems more valid in the, in a tree. Child of is not the language that we use in Python. That's the language of JavaScript. Okay, so we're collecting all the child of node from graph. Now if this child is not equals to parent, because you don't want to go back, there is a two-way relationship, so you want to skip that. Always remember that you have to you make sure you're not getting stuck in this loop. So at this place, what are you going to do? You can collect all the representative from the child might bring some representative to to the parent. So let's collect it into R. You will be getting it from DFS. In the DFS you will send the child, and then as a parent you will send the node. That is the that will become the parent of this child. Now this R, we will add it to basically our total representative right here. Now the fuel, let's collect all the fuel would be, this fuel would be added to basically our total fuel. And how do you get this total fuel? You will get this by basically, you know, have this all the representative. This is not result, by the way, this is rep representatives. So rep represents all the representatives. So this rep we have total rep. I'm just gonna call it total rep, make more sense. Okay, total rep. So this total rep, total rep would be, oh my god, I haven't copied this. We'll add R to total rep. This total fuel will be basically this total rep divided by seats, divided by seats. But before that, let's convert it to you know, ceil, and that ceil we're gonna convert it to basically integer. Okay. Now what we're gonna do is we have added it to basically our, I forgot that this is an array. Okay, we are adding it basically to our 0th element so that we can access it. You can also make it non-local. That's what a lot of people do. Declare it's anywhere and then make it non-local, and then basically do that. So here I will be basically returning total representatives that I have collected plus 1, because I am adding one representative as the node will be adding one representative, because the current city also has one representative, although it's collecting all the representatives from the child nodes. Now that will be it. I think now let me zoom out and let's see. That's the entire code. I hope you can see it like all in one go. Yeah, so now let's try to run it. We are kind of making a mistake right here. So this is not what we want to do. We don't want to calculate for the total representative. We just want to calculate the cost for the representative I have just collected from the children node. So at this place, I'm collecting the total representatives like to return later. So here it will be just R, and maybe, you know, it's better actually to have this line in the end. Right, so now let's run it again on the examples, and I guess this time, yes, exactly. Okay, let's submit. Awesome. So let's write down the time complexity. So here we are running the DFS, and DFS takes you know, if it is a balanced, you know, balanced tree that's given to us, then it will be kind of log n, but worst case the tree might be just, you know, just one only you know, linear data structure, you know, just pointing like a linked list, just long linked list, you know, so that's when it will be big O for n. And then space complexity would be, are we storing any space here? Well, other than stack, yeah, that, you know, because it's a recursive function, you know, so this could also go up to worst case n as well. Only the stack implicit space complexity that we were talking about. Okay, all right, let's go back to AlgoYogi, mark this problem solved. See you guys later in the next problem. Bye bye.